When you are dealing with antennas, you know that most of the parameters like input power, output power, gain, directivity, everything is specified in dB. So in this video, we can analyze why dB scaling is more important for antenna parameter definitions. dB means decibel. It's a logarithmic scale. If we have a value on the linear scale, and if it is that power value, if we have to convert that into dB, this is the equation to convert. It is 10 log 10 of linear scale value. And if you have that amplitude value like voltage and current, if you have to convert that into dB, this is the equation that we have to use. Let's see some of the characteristics of dB scaling. So here, this table, you can see the linear scaled value, which is converted into dB scale using this equation. Here, I have used the power values. That's why this equation 10 log 10 of linear scaling. So one of the characteristics is here, if you observe in dB scale, this increment of 10 dB, that is, here you can see when I consider 0 dB, 10 dB and 20 dB, it is an increments of 10 dB. But in linear scale, it will be a tenfold increase. So here you can see 0 dB corresponds to linear scale of 1, and 10 dB corresponds to linear scale of 10, and 20 dB correspond to linear scale of 100. So this 10 dB increase in dB scaling means tenfold increase in the linear scaling. So here you can see 1 into 10 equal to 10, 10 into 10 equal to 100. So this is one of the characteristics. Another characteristic is huge variation in power scale can be represented by short range of scale in dB. Here you can see when I consider the linear scale from 1 to 10,000, you can see that in dB scale it's only getting incremented from 0 to 40 dB. So this huge variation can be converted into logarithmic scale so that we can have a short range of values, because this will be mainly useful in our antenna cases, because we usually specify our antenna has a side lobe level of minus 20 dB. So we are just specifying it is less than from 0, it's less than 20 dB. But in linear scale, it is representing 100 multiples. So by using the dB scale, we can represent the values in short range of scale, so it will be more visible to visualize and understand. Next, we can analyze another characteristics. This is one of the most misinterpreted thing. So here we are going to consider two values, 3 and 30 dB. Here we won't be able to say that 30 dB is 10 times more than 3 dB. Here we won't not be able to say that in dB scaling. It is not possible to have a direct comparison like 10 times in dB scaling. For that, we have to consider the linear scaling. So here you can see that 3 dB corresponds to 2 and 30 dB correspond to 1000. So it means that it is 500 times more. That means that 30 dB is 500 times more than 3 dB, not like 10 dB. So it won't be possible to have a direct comparison in dB scaling, like it is a multiple of something like this or something like that. For that, we have to always consider the linear scaling and consider that and then convert into dB. Another characteristic is if the multiplication in linear scale will be converted into addition in dB scale. So here you can see that if I am going to multiply 2 and 3, it will become 6, and in dB scale it is corresponding to addition 3 plus 4.77. It is not multiplication, it is in addition. So the multiplication in the linear scale become addition in the dB scale. Similarly, division in linear scale is subtraction in dB scale. So if you are going to divide 10 by 5, it is like 10 minus 6.99. So we can see that 10 by 5 is 2. So that means 10 minus 6.99 is 3.01. That is, division in linear scale becomes subtraction in dB scale. Let's see why dB scaling is most important for antenna parameters like realized gain. So here I have considered the realized gain in linear scaling. Here you can see that I can see only one main lobe, no other information like side lobe or nothing is visible with this scaling. So this is the dB scaled version of the same realized gain. So here you can see that lots of information like side lobe level, back lobe level, everything is visible within this scaling dB. That means in linear scale, the range may be very high, so we won't be able to see every information with some specific scaling. So if we are going to convert that into the dB scaling within a limited scaling, we will be able to see every information. That's why we are always specifying gain in dB so we can have the most visible information like side lobe level, back lobe level, and everything from the dB scale value. So another example is this is the equation to calculate the link budget. Here this is the received power which is related to the transmitted power, transmitted gain and receiver gain by this equation. So if we are going to have everything on the linear scale, we have to multiply everything and has to calculate the values. But if we have that values in dB scale, it's very easy to calculate because we have seen that multiplication in linear scale become addition in dB scale and division become subtraction in dB scale. So we we can easily calculate the link budget using the dB values. That is one of other important characteristic. I hope you get some idea about why dB scaling is most important for antenna parameters. So if you find any of our videos useful, kindly support by liking, commenting, sharing, and subscribing. Thank you.